Okay, so we'll go ahead and get started here. And one change I would like to make is maybe this. Okay. So, looking up at these four reactions, where would you like to start? Just at the top and work down. So we will start with the blue first. All right. The reason we say that is because of the following. If we're going this direction, what would you presume that the blue arrow is illustrating? And why you're correct when you say decomposition, why is that? Because you are splitting this apart where you have a definitive compound here that's being broken down, and in this case, into associated pieces. Now, you can have more than three products in a reaction. That can happen, okay? In this case, there's only two. So what is it with this arrow? If it's going back this direction, then it's a synthesis reaction. And we call this reaction just reversible because you can go one way or the other. But we'll just stick with the blue going in this direction. We know that that is a synthesis, a decomposition reaction. If we remember from physical science, what would you guess those blanks represent? Yeah, it's coefficients that go in front of each one of these. So right now it is 1, 1, and 1 because we haven't changed anything yet. And sometimes you don't have to change anything. Okay? So, where would we like to start with that? You can aluminum or oxygen, either one, doesn't make any difference. Okay? So these are odd, these come in pairs. So we have an even number and an odd number. How do we get that to an even number? So if we multiply this by 2, that changes our aluminums as well, but it gives us 6 oxygens. Okay? So how do we get 6 oxygens over here? If we take it times 3, our oxygens are now balanced. Just one small aspect we need to do for the aluminum. And 2 times 2, because these coefficients get distributed through the entire compound, so that gives us 4. So it started out as 1, 1, and 1. So we changed these, and now we end up with, okay? We're moving up.
Yeah, I couldn't see back there.
Oh, okay. Then, the next part we would do is remember we would start with our negative ions if it's referring to oxidations and reductions. So we have to start here. We'll just start with this compound. So all of this balances out because this oxide or oxygen has a what charge? -2. What does this aluminum have for a charge? +3. So 3 times 2 is 6. 3 times -2 is -6. So that's why it balanced out. So through this process of decomposition, what has happened to this aluminum? Did it gain or lose? It lost electrons. Okay? So then what we see, this is a 0. Okay? And then what about this oxygen then? That's also 0. Okay? So then, when we look at the charges, what happened to the aluminum? Yes, it went from 3 to 0. Did it get reduced or did it get oxidized? It got reduced because it went from 3, 2, 1, and then to 0. Okay? So we have oxidation and we have reduction. Okay? So it started at a +3 and it went down to 0. So it got reduced. Okay? Then when we look at the oxygen, does this charge get bigger or smaller? It gets bigger because 0 is greater than -2, so therefore this had to have been oxidized, or the oxygen. All right.
Mr. McKinney, I think we need a definition on reduced.
Okay. You need a definition on reduced. Okay. I'm confused, so I'm going to hit pause for just a moment. All right, so we're back. Now, moving forward. We've got this balanced. We've got it classified. We can move forward. Okay. With this reaction, what is your best guess? And does, yes. No, we'll skip the agents for now. Okay? Now, what is your best guess on what this equation is? Okay? And we don't want to say guess, maybe that's a bad term. How do you know that you've correctly identified this as a single replacement reaction? They're switching. And how many switches have taken place? Just one. Now, will this reaction take place for sure? Your activity series would tell you that. So in doing so, when we look at this, because we're setting the stage for what we call double replacement reactions, and what I want you to think about is locate this ion. Okay. Now that's not on today's assignment that's due for next week, but like I said, we're setting the stage for moving forward. So now what I want you to do, this doesn't pertain to the activity series. We already know what the name of it is. It's here in the middle. What can you presume that all nitrates, it doesn't matter if this is ammonium nitrate, aluminum nitrate, cadmium nitrate, silver nitrate. Yes, that's all true that that's a -1, but we had mentioned we're talking about this middle portion now. So what does that mean when you find NO3? All nitrates are soluble, okay? Because that's going to be an important aspect when you learn reactions in chemistry, because some solutions or aqueous solutions become insoluble. But nitrates are extremely soluble. But again, that's double replacement reactions. That's where these become more important. From yesterday, AQ just means an aqueous solution. That's what this would be, an aqueous solution. What about potassium? Which state of matter would you think that is? Is it a gas, a solid, a liquid, or an aqueous solution? Potassium now. Correct. Now, how do we know that this isn't a liquid? Does this have water in it? No, so it's not, certainly not a liquid. Is it mixed together with another ion? No. So therefore it can't be an aqueous solution, and we know by elimination that this is not a gas, so this would have to be a solid. Okay? because again, that's such an important part of learning double replacement reactions. Okay, so again, does this reaction take place?
Yeah.
How do you know?
Potassium's above.
Okay, so this solution that we have, this is higher in the activity series. We wouldn't have to necessarily write potassium in there. There's a whole bunch of other ions that we could write. So once we find calcium in our activity series, okay, what else could we put besides potassium? You could use certainly lithium, barium, and that's it. Okay, everything else is below that in the activity series. So then, how could we change this to say we're going to get no reaction? We could put manganese here. Why are you correct when we say no reaction if we put manganese? Because this is above manganese in the activity series. Okay? So this just isn't strong enough to replace that metal ion. So going back to what we have, we had potassium here. Okay, then this is single replacement. Now, when you balance these,
Some days I feel like I'm on this side. They're just figuring things out.
I'll nod my head to an agreement. Yeah. That must be important what we're talking about back there. It is. Okay, it's more important. Okay, and maybe it is.
I already have this problem solved.
Okay, good. You can separate your elements here, but what's a better way to solve for this ion when balancing? What did we do in physical science? You might have done this. You might have done that. Okay? And the majority of the time, I would recommend that you do that, keeping your nitrates together, if you choose to write these out like this. But you don't have to, because this gets solved pretty quickly when we say we've got 2 nitrates on this side, because that's the only place we can start, and this only has 1 nitrate over here. So therefore, what must we put in front of here? Okay? So then we've got 2 potassiums and 2 nitrates. 2 nitrates, but only 1 potassium here. Put a 2 there as well. Okay? Now we've got everything balanced. Okay? Now, when we look at this, what does calcium have for a charge? What does nitrate have? What does potassium have for a charge? Now careful, just don't blurt out the first thing you think of. 0. Okay? And then what does potassium have for a charge here? Now it's got what? Well, nitrate and calcium. It's not that we would do this, but why could we, as far as doing this portion here, why would we do that? What's true about the nitrates on both sides? Because look at what calcium did. It was +2, it's 0. What did the potassium do? It's 0, now it's what? Okay, but then what's true about the nitrate? Yeah, it's a spectator ion. It didn't do anything. Okay? Just because you have 2 of these here, that doesn't matter. It didn't matter when we did it with the aluminum. It's not going to matter when we do it for here either. Okay? So that's a spectator ion. So now, who is oxidized? Right? Because this lost an electron, So this is now oxidized, but potassium. So what is reduced then? Calcium is then reduced because 2 is larger than 0. All right. Of these next two, do you just want to keep going in order? Or what? Okay. Go ahead and finish that reaction. So go ahead and finish this reaction. So as we look at this, we have cobalt chloride. We've got what type of cobalt? What type of cobalt? What type of cobalt? Cobalt 3 chloride. So we look at this on our activity series, what we're saying, we've got this solution of cobalt 3 chloride. We want a reaction to take place with tin. But where is tin in reference to cobalt? It's below this. So this cannot replace the cobalt. So therefore, we would do this on the other side. It's not going to react. And then finally, with this bottom one, what type of reaction do you think it is? It's a combustion reaction. Okay? Okay, here's our combustion reaction. So in order for something to burn, what must it have? It must have oxygen. So then what's given off as a byproduct? Okay. All right. So now, as we look at this, this is probably the most difficult one until it would appear to me that some of you are more comfortable with this now, unlike yesterday. Okay? It just seemed like for those of you who were here in the 3rd hour class, one of your classmates isn't here. I had the 2 papers for her as requested, and I went like this, handing it. I said, don't hit me, don't hit me, okay? Handing out the paper to them, because making this in reference to yesterday. Is this equation difficult to balance, yes or no? There's really no correct answer for that, because if you recognize something right away, you will make it a lot easier on yourself. What would it possibly be? How can you make this easier on yourselves? Why are you correct? Okay, now keep in mind, if we did something like this, okay, notice these are 2 different organic families. Okay, if this is an alkane, which it is, that's fine. Go ahead and double that. But if it's an alkene where your hydrogens are twice as many as your carbons, you're also going to want to double that, even though that's an odd number, because those are different organic families. But nonetheless, they still would go through combustion. So we do our carbons, 2 times 4. So that must mean we need 8 over there. Always do your oxygens last. Okay? So how many hydrogens are on the left side? And how do we get, we only have 2 over here. Okay? So now, for our oxygens, 8 times 2, 16, 10 times 1. So we've got 16 plus 10 is 26. We got 2 over here. 26 divided by 2 gives you 13. Okay? Now, this is why this is the tricky aspect to this. Okay? Because carbon is the most diverse element that we see on the table. One, because it's in carbon. It's in column 4. It might say that on your periodic table, but certainly when we look at over here, we can see that carbon has a whole bunch of different charges it can have. -4, +2, and +4. Okay? But in this case, the reason that we know that hydrogen is a positive charge here is because there is such a compound as this. It's called a hydride. Okay? That's where this would be -1 and that's +2. But that's obviously not a hydride because it's not a metal with hydrogen. These do exist, okay? But that's not the case here. So therefore, that's the only time hydrogen is a negative charge. So if that's the case, which it is, this hydrogen is +1, okay? Therefore, how many total positive charges do we have here? You would have 10. Now the reason that that is significant is because if we write this out, if you remember from your organic portion 2 years ago, okay, we've got 3, 5, 7, there's our 10 hydrogens, each one of those hydrogen having a +1 charge. Well then that must mean that we have carbon with adding up to +10. Okay? Well, if that's the case, well then we've got a negative charge here. I have to look at this. Because it doesn't say it on there. Carbon -3, carbon -3, carbon +2, carbon +2. Now, I did that wrong. The numbers are correct. -3, -2, -2. There we go. So now, adding all of these negative numbers together, what do we get? 3 plus a -2 is -5. 3 plus a -2, -5. -5 plus -5 is -10. So that must mean that that is how this balances each other out, -10 and +10. All right. Now, let's look at our oxygen. What is the charge of this oxygen? Okay? We always say go by your negative charges. We're not going to deal with water here. We're going to use carbon dioxide. Okay? So what does oxygen have for a charge? Over here. What type of 2? -2. This carbon has a what charge? Don't look at that side. +4. Because -2 times 2 is -4. 4 times 1 is +4. Okay? Now we can proceed with this. Okay?
Wait, how do you get the -10 for carbon? You use 4 carbon and hydrogen.
That's true. But when you look at the structure here, we know that hydrogen's got a +1 charge, correct?
Yeah.
Okay. Well, when we draw out this structure, if this hydrogen has a positive charge, which it does, okay, that would be +3, correct? Okay. So then this carbon's got a -3 charge. This has 2 hydrogens, each one of them having a +1 charge, giving you -2. Same thing here. And then 3 hydrogens for +3, and then a -3 for the carbon. And then Right here, I know we answered it correctly because I was looking right at you when you added those correctly. A -3 plus a -2 is -5. Okay? A -3 plus a -2 is -5. Both of them added together, that's where your -10 comes from.
So you don't.
So now, probably this -10, did that number get bigger or smaller? It got much, much bigger. Okay? Then we could look at the oxygen. Did that get bigger or smaller? It got smaller, so that was what? That was reduced. And then, there we go. All right. So the next thing we need to do, that we did, we just didn't write it in here. 2, 13, 8, and 10. All right. So we have a little bit of time yet, so I want to go ahead and pause it there. And you have time to work on these. What does it say? 10, 25, 10. I hope not. 11:25. When is that?
Tuesday.
Next Tuesday. Okay? So what are we doing tomorrow? You have time to work on these. All right. So that's all I have. We'll catch up to you next time.